Okay, then I will speak this English. All right, I'm Wei-Hao Wang from ASIAA. Thank you for giving me this opportunity to present our recent results from studies, which stands for Scuba 2 Ultra Deep Imaging EAO Survey. I will briefly tell you what studies is, and then present several recent results from our survey. Comparing to NEP, studies is actually a pencil beam survey. We use Scuba 2 to cover 2 pointings, one in Cosmos, the other one in Subaru X and deep field, and each of them is Scuba 2 dicey imaging mode. So the field coverage is much smaller than NEP. However, we try to go ultra deep with studies. In these 2 JCMT large program, we will have more than 600 hours of total integration, and in each field, we will reach the confusion limit at 450 micron. And hopefully, that means we can detect objects that's 10 times deeper than what you can detect with Herschel length field observations. Since this is a JCMT large program, we have scientists from all the JCMT partner regions, and we have more than 140 people in our team. To show you what it is like, I will use our Cosmos field as an example. Our survey in the Cosmos field was just completed earlier this year. So on screen, you can see the 2 square degree field of the Cosmos covered by another JCMT large program S2 Cosmos at 850 micron. Studies only look at the very center of the Cosmos field like this. Now you are still looking at the 850 micron, but at the center of the Cosmos field. And now I will show you the 450 micron map. This is our 450 micron map from studies and also from archival data. You can see it's not only much deeper than the 850 micron image, but also the resolution is about twice higher. This gives us a capability to detect sources that are confused in 850 micron images. We can also compare our 450 micron maps with Herschel 500 micron maps. Here I show our 450 micron maps. Each circle is a detected object. Now you will see the Herschel map. Again, the circles are our detected objects at 450 micron. So again, you can see that the resolution of our 450 micron map is much higher. And many of our detected objects are either confused or just undetected in the Herschel image. So in the Cosmos field, we collected almost 500 hours of integration. About 1/3 of them come from the JCMT archive from previous programs, including the cosmology legacy program. 2/3 of the 500 hours comes from our own observations. We reached a sensitivity of better than 0.55 millijansky at the field center. At 450 micron, this is incredibly deep. And we detected about 450 sources at 3.5 sigma level, and our field coverage is roughly 300 square arc minutes. With data like this, of course, then you can do lots of studies using studies data. So I will show you what our studies are. The first one is you can construct number counts to ask how many sources you detect within each flux beam. So the white points are our latest results using the 500-hour Cosmos map. And you can see that comparing to previous 450 micron counts published by Jim Gitch and Clayton Casey, we are about 3 times deeper. in the very faint end, at about 1 millijansky, there are previous detections, previous measurements of the counts from strong lensing clusters, and also our own constraints from fluctuation analysis. You can see that they roughly agree with each other. We can also compare our counts with Herschel counts. However, Herschel is confusion limited at about 20 millijansky. So Herschel can only directly detect sources brighter than this, and fainter than this, the counts are derived from 24 micron prior. So we suffer from all kinds of biases. And you can see that the Herschel counts don't really agree with Scuba 2 counts, no matter it's from Cosmos or from other fields. And if we integral down the counts to the flux level of about 2 millijansky, we can recover from 30 to 45% of the 450 micron background measured by the Kobe satellite. And if our count slope continues to fainter flux level, we predict that we can fully resolve the counts at a flux of about 0.5 millijansky. That's how deep you need to go if you want to detect all objects that produce the far infrared background. And there is no hope with Scuba 2 to do this unless we do deep imaging in strong lensing field. So you may know that there is another Scuba 2 large program in lensing cluster field. Hopefully that will bring us down to 1 millijansky or even deeper. One of our earlier papers is to study the rest frame optical morphology of the 450 micron sources. This was done by Yu-Yan Chang, who I believe is also in this conference. We look at the Hubble near-infrared data in the Cosmos field from Kendall's survey, and several of us just look at the picture and classify the morphology without any fancy machine learning algorithm. We found that once we matched the star formation rate of our samples, no matter they come from 850 micron selection, 450 micron selection, or just normal optically selected star-forming galaxies. Once we go above about 100 solar mass per year, pretty much everything we see are either merging galaxies or galaxies with irregular morphology that hints about galaxy interaction. So this perhaps tells us the ultraluminous infrared galaxies, the very intense star-forming galaxies, no matter they are detected with dust emission or not, they are related to galaxy interaction. In another paper we published this year, we further combine the morphology with the main sequence or the star formation rate, stellar mass ratio, and also dust temperature. In this diagram, you see that we classify disk galaxies, spheroidal galaxies, and merger galaxies. The merger ones are those in green. The x-axis delta ms is the distance of the galaxy from the main sequence. If they are on the main sequence, they are regular star-forming galaxies. If they are far above the main sequence, they are star-bursting galaxies. In this diagram, we see that when galaxies are far away from the main sequence, first, they tend to be mergers. And second, they also tend to have higher dust temperature. One possible explanation to this is that, again, the star formation or starbursts in these systems are driven by the merger activities. And some simulation shows that once that happens, once you have a nuclear starburst, you have higher dust temperature. So this probably also supports the merger-driven scenario for dusty galaxies or starburst galaxies in general. Also in the same 2020 paper, we used about 200 450 micron selected galaxies to construct the far infrared luminosity function. And you can see that probably there is nothing surprising here. When you look at the ultraluminous population, they only show up at redshift greater than 1.5 or 2. And when you look at lower redshift, the low luminosity systems really dominate. So this is not surprising. You see this in all the other luminosity function studies, even in optical or X-ray surveys. What's interesting here is that we are the first far infrared survey that can put constraints on the fan-end slope. If you look at previous high redshift far infrared luminosity functions, no matter from ALMA or from Herschel, they assume the fan-end slope. Now we do not need to make such an assumption. We can directly measure it. And this is from our study sample 2 years ago. Now our sample size is about twice larger, so I hope in the future we can even put a tighter constraint on the fan end and maybe push it to higher redshift. We also compare our luminosity function with models. Here I show several models, like the empirical model from KCLO, semi-analytical models, and also Aoyama-san's or Hirashita-san's cosmological embodied dust simulation. And you can see that the empirical model or semi-analytical model are more or less okay when they compare against our infrared luminosity function. But once you really want to put real physics into the simulations, you start to have troubles. The model do not match the observations. In Aoyama's paper, 2019, they argue maybe this is about the treatment of AGN, but we really don't know. What I really want to tell you is that we still have a long way to go to understand this population once we want to put real physics into it. And it's a challenging problem. So while we are pushing our measurement of infrared luminosity function, I hope our theoretical friends can also push their models, and maybe after 1 or 2 years, we can come back again to compare our results. In this latest paper published by Udne, unfortunately I cannot pronounce her last name. She's a graduate student from Durham. She did this SED fitting from UV to radio using MACFIS on 450 micron sample from studies, and also 850 micron sample from AS2UDS. So she compared the dust properties and also infrared luminosity and the evolution of space and the spatial density of these two different populations. One thing I want to highlight is that in terms of stellar mass, the 450 micron selection and 850 micron selection do not really select very different galaxies. However, you can see that they have different dust mass, they have different dust temperature, and even this different extinction. And maybe some of the differences are driven by the difference in size of the two populations. And now, the last topic I want to introduce is how we connect dusty galaxies to dark matter halos. And you know that to do this, you need a very large sample. Just a few hundred galaxies will not be enough. So what we do is to use the machine learning technique to enlarge our sample of dusty galaxies. This is the 2 square degree cosmos in the optical, and in the center is our 450 micron coverage. So you can see that we only cover a small part of the cosmos field. In the whole cosmos field, there are more than 1 million galaxies in the optical, and then we only have maybe 300, 400 450 micron selected dusty galaxies. So what we want to do? What can we do with the almost 1 million optically selected galaxies that do not have 450 micron coverage? So as I said, we use a machine learning method. We use our sample as a training sample, which contains about 160 450 micron galaxies and more than 4,000 optical galaxies in the same field. And using this training sample, we want to classify some emitter galaxies or dusty galaxies from the almost 300,000 optical galaxies in the 2 square degree cosmos field. We did this with various machine learning algorithms, and you can see that each of them have quite different performance. At the end, we then did this XGBoost method, which gives an F1 score of 0.6 and precision and recall all about 60% to 70%. If I have time, I can explain more to you, but now let's just use this result and try to see what we can do. So as a result, we can select almost 600 dusty galaxies from the Cosmos field. We use ALMA data from the archive and also shallower 450 micron coverage in the field to verify our selected dusty galaxy candidates. Then with 600 galaxies, now you can do clustering analysis to measure their clustering and compare with passive galaxies or other star-forming galaxies. The result is that we found our 450 micron selected galaxies have a dark matter halo mass of about 2 times 10 to the 13 solar mass. And if you compare that with 850 micron selected galaxies, you will see that this number is a little bit high. And to be honest, I don't know what's the reason. You may expect 850 micron galaxies to be more massive than 450 micron ones. This is not what we found here. Obviously, there are more works to do. So let me summarize this by saying that what we learned from studies from a small sample of a few hundred galaxies can still help us to understand things like clustering properties or dust evolution or even fine nasty functions. So with the wide field coverage of NEP, I believe people here have lots of interesting things to do. And in the future, I hope we can talk and collaborate with each other. Thank you.
Thank you very much for the very nice talk. Local people, anybody have a question? Okay. Tomo-san has a question. 600 over 10 to the 5 is number fraction. Is this why they are more messy?
Which part?
So let me follow up. So your training sample had only, I forgot the number, but what is it, 164 out of 5,000, right?
Right.
But compared to that fraction, 600 out of 3 to the 10 to the 5 is much smaller fraction. So I thought, first question, why? And then second question is, this may be why your 450 sample is more massive than 850 micron, because you're selecting smaller number.
Perhaps. Another reason is that our coverage our scuba 2 coverage is not very uniform. It's very dense at the center, and the sensitivity gets lower and lower to the outside. So you cannot simply just use the number ratio to infer what you are going to find here.
Well, but this is training sample, right? So, the optical depth is the same, right? Then your selection sample fraction should be the same, because optical is uniform.
Not really.
Does it make sense?
The sum-unit sample is not uniform. It's not flux limited.
You mean optical sample?
Sum-unit sample.
Okay.
So it's possible that here we tend to pick up the more luminous ones.
Wait.
As you said.
Your machine learning selection is based on optical, right? And then you're scaling from this deep field, so it doesn't matter scuba 2 is deep or not. You're scaling from there.
But this 160 sources contain different sources of different flux.
I know. It doesn't matter. Optical
Small
is
number
a
of
common
very
part.
faint sources and large number of brighter sources.
Yes, but optical sample there and the other part are same, right? Then fraction should scale.
I don't think so.
Okay.
Because if you look at the ratio between optical sample and sum-unit sample, that ratio changes from the center to the edge.
Yes, but the optical sample there is the same on the other outside of the area, right?
I don't quite agree, but maybe we can talk about this.
Yes. But then, could that be the reason why 450 sample is more massive? Because you're
it's possible.
Maybe selecting more massive, smaller number.
another possibility is that our machine learning algorithm do not give you 100% precision, do not give you 100% recall. So our sample is always contaminated by unknown optical gases.
But that you can test in a training region. That you must have had the results.
Again, they are different.
Okay.
Okay, seems like the time's up. So we have a lot more questions in Slack. Maybe you can answer later. So you